Imagine a single particle, an electron, a speck of matter smaller than dust. Fire it toward a screen and it behaves like a tiny bullet. Fire another and another, and suddenly it paints a pattern no bullet could ever make, a wave signature, as if the particle had somehow split itself, walked two paths, and interfered with its own ghost. How can reality allow such a contradiction? How can something be a particle and a wave at the very same time? Imagine you are standing in a vast hall of mirrors. Every reflection shows you as solid, tangible, undeniable. Yet when you step closer, the image wavers like smoke, like ripples on water. One moment you are a person, the next a shimmering distortion. That is the essence of the riddle physics stumbled into, the things we thought were most certain. Light, matter, the very fabric of existence, refuse to play by a single set of rules. Wave, particle, two words that seem irreconcilable. A particle is a point, a grain, a speck of matter you can imagine touching. A wave is a spreading influence, a disturbance, a pattern that stretches and diffuses. And yet nature insists that the same object can be both, not metaphorically, not figuratively, literally. Depending on how we look, the universe wears two faces, and it never lets us see both at once. This paradox is not a curiosity tucked away in some obscure corner of science. It is the foundation of modern physics. Your body, the air you breathe, the light from the stars that has traveled across billions of years, all of it is caught in this impossible duality. Every atom in your body, every photon striking your eye as you watch this, is both a localized particle and a rippling wave. It should be nonsense, and yet it is true. The question is, how did we discover this? And why does it matter? For centuries, science built itself on certainty. Newton showed that planets and apples alike obeyed the same laws of motion. Mathematics gave order to the heavens. The Enlightenment was a triumph of rational clarity. The world could be measured, calculated, understood. And then came a series of experiments that shattered that clarity, forcing physicists into a twilight zone where the solid ground of certainty dissolved into probability and paradox. The riddle of duality is not just a story about physics. It is a story about human perception, about the limits of reason, about how far we can trust our intuition. Because if matter itself can wear two masks, then what else about the universe is stranger than we can imagine? Consider this. When you think of a wave, you think of the ocean. A rhythmic motion that rises and falls, spreading energy without moving water molecules across the beach. When you think of a particle, you think of sand, each grain distinct, colliding, bouncing, individual. To say that something can be both is like saying that the same thing is both the tide and the stone, both the motion and the mover. It defies common sense. Yet nature is under no obligation to obey our sense of reason. This paradox revealed itself first in the study of light. For centuries, light was one of the greatest mysteries. Was it a stream of particles like Newton imagined, tiny corpuscles shot out from the sun and bouncing off objects? Or was it a wave, like Huygens believed, rippling across some unseen medium that filled the cosmos? The evidence kept shifting, the debate never fully settled. Every explanation was partial, incomplete. Light seemed to mock human attempts to pin it down. And then, in the early 19th century, a simple experiment pulled the rug out from under science. Thomas Young, with little more than a beam of light and two narrow slits, revealed an interference pattern that could only belong to waves. The verdict seemed clear. Light was a wave. Case closed, or so it seemed. But that was only the beginning of the story, and the universe had a cruel twist in store. You see, every time humanity thought it had solved the mystery of light and matter, reality came back with a contradiction. Like a trickster god, the universe offered answers that dissolved into deeper riddles. Each discovery made the picture stranger, not clearer. By the time Einstein entered the stage, light was forced to wear both masks at once, photons, discrete particles of energy, behaving with the rhythm and interference of waves. The contradiction wasn't an error in our instruments. It wasn't a failure of imagination. It was how the universe truly worked. And if light could do this, why not matter itself? This is where the story deepens, because it's not just photons and electrons that play this dual game. Even larger objects, molecules with dozens of atoms, can interfere with themselves like waves. Imagine a soccer ball being kicked toward a wall with two holes, and somehow, impossibly, that soccer ball going through both holes at once, then interfering with itself on the other side. Ridiculous. Impossible. Yet it happens in the quantum world, invisibly, beneath the surface of our everyday lives. Every second you are living inside this paradox. The atoms in your body are described by wave equations that spread across space. Yet when you touch your skin, you feel solidity, particles locked together. Which is true? Both. Neither. Reality does not fit into our categories. This duality is not just a scientific puzzle, it is a philosophical earthquake. If the building blocks of reality cannot be neatly labeled, what does that mean for truth itself? Can something be two things at once, not because we lack information, but because that is its nature? What does it mean for the boundary between opposites, wave and particle, certainty and uncertainty, reality and illusion? And here is where the story becomes unsettling, because this duality is not passive. It does not merely exist. It responds to us. When we observe, particles behave differently than when we do not. When we measure, waves collapse into points. When we do not, they spread across space. The universe seems to care whether we are watching. It seems to know. Already the foundations of science were trembling. Already physicists were forced to admit that the old picture, a universe of solid particles obeying mechanical laws, was incomplete. Something deeper was at work, something stranger. The riddle of duality had been set. But to follow its trail, we must travel back in time, to the very beginning of science's struggle to explain light. To the days when giants like Newton looked to the stars and asked, "What is light? A stream of particles, or a wave rippling through an invisible sea?" The answer, of course, would turn out to be both, and neither, and far stranger than they ever imagined. Because the riddle of duality is not simply about particles and waves. It is about the very nature of reality, and about how deeply we are entangled in it. To understand the riddle of duality, we must step back in time, to an age when the word science was still new, when natural philosophers peered into the workings of the cosmos with little more than candlelight glass lenses and boundless conviction. The 17th century was an age of revolution. Newton had revealed that the same force which pulled an apple to the ground also held the planets in their orbits. Order seemed to reign, written in mathematics, carved into nature's design. The world, once a mystery, now looked like a mechanism, predictable, measurable, eternal. But light remained a troublemaker. Isaac Newton, the towering figure of his age, was certain that light must be made of particles. He called them corpuscles, little bullets of illumination shooting out from the sun and striking the eye. It made sense. After all, particles explained reflection, light bouncing like a ball off a wall. They explained refraction, light bending as it entered water, like a marble changing course as it passed into a thicker medium. Newton's genius gave his theory weight. If he declared light a particle, who would dare argue otherwise? And yet across Europe, another voice insisted otherwise. Christian Huygens, a Dutch scientist, saw light differently. To him, light was not a stream of bullets, but a wave. Like ripples spreading across the surface of a pond, light expanded outward in every direction. This wave model explained why beams of light seemed to bend around edges and spread after passing through tiny openings, behaviors particles could not easily mimic. Here lay the first great fracture. Two visions of reality, both elegant, both incomplete. Imagine the drama of that era. Newton's shadow loomed so large that dissent was dangerous. His reputation, his discoveries, his very presence commanded respect. And yet Huygens held firm, defending the wave model with quiet persistence. Two men, two visions, each with experiments and arguments to back their claims. Science was split between corpuscles and waves, certainty and fluidity. For over a century the debate raged. Experiments piled up, each seeming to strengthen one side while raising questions the other could not answer. Newton's authority kept the particle view dominant in England, while the wave model found more sympathy in Europe. It was not merely a disagreement about optics. It was a philosophical war about the nature of reality itself. Was the universe built from tiny, discrete pieces? Or was it a continuum, a fabric of endless ripples and oscillations? Think about the stakes. If light was made of particles, then perhaps everything in the cosmos could be reduced to indivisible grains. Predictable, deterministic, mechanical. If light was a wave, then reality might be fluid, holistic, inseparable. This wasn't just a question about illumination, it was a question about what the universe was. For over 100 years, humanity could not decide. Both models worked, to a point. Both explained some aspects of light and both failed at others. It was as if reality were teasing, offering glimpses but never revealing its true face. Imagine the confusion. A scientist measures reflection and sees a particle. Another measures diffraction and sees a wave. The same phenomenon, two incompatible truths. Surely one must be wrong. Surely reality must choose. And yet, it didn't. This tension built like pressure behind a dam. For generations, the question lay unresolved, waiting for the right experiment to crack the wall open. The 17th and 18th centuries gave us two visions of light, each powerful, each incomplete. The world seemed to hold its breath, as though preparing for the moment when the universe itself would give its answer. And that answer would come not with a thunderclap, but with the quiet persistence of a single man, Thomas Young, who dared to shine light through two narrow slits. But before we reach his decisive revelation, pause to consider the irony. Newton's universe was neat, ordered, rational. Particles made sense, waves made sense, but never both. To accept both was to invite contradiction, and contradiction was the enemy of truth. And yet, the truth of nature would turn out to be exactly that contradiction. How can one object be two things at once? Newton and Huygens could not imagine it. Their minds, brilliant as they were, could not cross that bridge. They demanded certainty, a single answer, and nature, with quiet indifference, refused to give it. The debate over particles and waves was not merely academic, it was a rehearsal, a foreshadowing of the chaos to come. For the next 2 centuries, humanity would discover that reality does not care about our categories, our insistence on consistency, our craving for order. Light was preparing to reveal itself as something deeper, stranger, more impossible than either Newton or Huygens could have dreamed. As we move forward, remember this: the greatest minds of the Enlightenment stood divided. They gazed at the same phenomenon and saw incompatible truths. That is not failure, that is foreshadowing. Because when Young performed his simple experiment, light would reveal itself not as particle, not as wave, but as both, and neither. And so the stage is set. The curtain is drawn. The actors wait in the wings, Newton, Huygens, and a beam of light that will betray them both. London, 1801. The city groans with the weight of the Industrial Revolution. Smoke fills the skies, gears grind in factories, and coal dust settles over streets lit by flickering oil lamps. Amid the noise and soot of progress, one man retreats into the quiet of his study. His name is Thomas Young, physician, linguist, polymath, a man whose mind seems unable to sit still. He has already deciphered ancient Egyptian hieroglyphs and probed the mysteries of human vision. But tonight he has turned his attention to the oldest enigma of all: light. Young has read Newton, worshipped Newton, but dared to question him. To challenge the great man's particle theory is to invite ridicule, and yet Young cannot ignore what his intuition whispers: that light behaves not like a rain of bullets, but like ripples upon a pond. And so he devises an experiment so disarmingly simple that it seems almost childish. On his desk sits a card, pierced with two thin slits. He directs a narrow beam of sunlight through them and lets it fall upon a screen. What he expects, what Newton's particles demand, is two neat bands of brightness like footprints where two streams of tiny bullets strike the wall. But that is not what he sees. Instead, the screen blooms with a series of bright and dark fringes, stripes of light and shadow alternating in perfect rhythm. It is the unmistakable fingerprint of interference, the calling card of a wave. One wave passing through the first slit, another through the second, overlapping, adding where crests meet crests, cancelling where crest meets trough. It is a pattern no stream of particles could produce. The room is quiet, but in that silence, science itself convulses. Young has shown that light is a wave, not metaphorically, not as a convenient model. The interference pattern is undeniable. A beam of light divided into two recombines as though it were ripples of water. Reality has spoken, and Newton, the untouchable master, is wrong. Or so it seems. One of the simplest experiments in physics reveals one of its deepest mysteries. Light, the very stuff that allows us to see, betrays us. It does not move like bullets, it moves like ripples, as though the universe itself were water and every photon a stone cast upon its surface. But then comes the deeper question: if light is a wave, what is waving? Water waves ripple through water, sound waves vibrate through air. What medium carries light? For Young, the answer is obvious: the luminiferous ether, an invisible substance filling the cosmos, transmitting light's vibrations. Waves demand a medium, and so a medium must exist. The ether becomes science's invisible scaffolding, holding the wave theory in place. And yet something about the double slit refuses to sit quietly. It is too strange, too haunting. Because hidden within that interference pattern lies the seed of an even greater paradox. Imagine, instead of sunlight streaming through the slits, we dim the beam until only one photon passes at a time. A single particle of light alone, with no partner to interfere with. You would expect the interference pattern to vanish, replaced by two simple spots where photons strike. But no. Even when released one at a time, photons accumulate on the screen to build the same interference pattern. Each particle, it seems, interferes with itself, as though it has traveled through both slits at once. Young could not have performed this version of the experiment in 1801, but the logic was there, waiting in the shadows. The double slit would become the stage upon which quantum mechanics unveiled its strangest act. But already in Young's time, it sent tremors through science. The double slit is not just an experiment, it is a mirror held up to reality, showing us that the world is stranger than we dare to believe. When two slits are open, light behaves as though it takes both paths. When one slit is closed, the behavior changes. The mere possibility of a second path alters the outcome. Reality is not what it seems, it is what might be. Young's contemporaries were stunned, even hostile. Newton's authority was immense, his particle theory was doctrine. To defy him was to challenge not just a theory, but a world view. And so Young's findings were ridiculed, dismissed, even ignored. The double slit, one of the most profound revelations in physics, languished in obscurity. And yet truth does not vanish. The fringes of light on Young's screen could not be unmade. They were burned into the foundations of science, waiting for the day when physics would be forced to confront them head-on. That day would come more than a century later when Einstein, Planck, de Broglie, and Schrodinger picked up the torch. But for now, the paradox slept in plain sight, like a riddle carved into the walls of nature, unread, but waiting. Imagine standing in Young's study, looking at that shimmering pattern of light and dark. It is beautiful, yes, but also unsettling. Because what it reveals is not just that light behaves like a wave. It reveals that the universe is willing to deceive us, to wear masks, to show one face in one experiment, another face in another. How can we trust our senses, our categories, when the universe itself slips between them? And here is where the double slit transcends science and becomes philosophy. What is truth if it can change when observed from a different angle? What is reality if it refuses to be pinned down to one description? To see Young's fringes is to glimpse the twilight zone where categories fail, where logic stumbles, where paradox reigns. This is why physicists still speak of the double slit with awe, even fear. It is the simplest experiment and yet the most inexhaustible. It whispers that reality is not binary, not particle or wave, but something deeper, something beyond our language. The fringes on Young's screen are not just stripes of light. They are the first footprints of a truth we still struggle to grasp. That matter and energy, the building blocks of existence, live in two worlds at once. And so the wave triumphs, for now. Young's fringes crown the wave model king, toppling Newton's corpuscles from their throne. For the next 100 years, light is understood as a wave rippling through the ether. Reflection, refraction, interference, diffraction, all explained with elegance. The world breathes a sigh of relief. Order has been restored. Certainty, it seems, is possible again. But certainty is always temporary. Because even as waves triumph, the ether and the invisible sea that waves ripple through will come under suspicion. And when the ether collapses, the ground beneath the wave theory will give way, and particles will claw their way back into physics. The story is far from over. In fact, the double slit has only opened the first crack in the wall. Through that crack, a flood is coming, one that will sweep away not just Newton, not just Young, but the very idea that reality can ever be fully known. For a century after Young's experiment, light was crowned as a wave. The interference fringes were undeniable, elegant, inescapable. At last, science had a model that worked, a way to explain reflection, refraction, diffraction, and even the shimmering rainbow upon a soap bubble. Waves had triumphed, and Newton's corpuscles seemed banished to the graveyard of discarded ideas. But a deeper question lingered, unasked, like a shadow in the corner of the room. If light is a wave, what is waving? A wave is not a thing in itself. It is a disturbance, a pattern riding upon a medium. Water waves move water, sound waves vibrate air. So if light is truly a wave, what invisible ocean does it ripple through as it travels from the sun to Earth across the void of space? Physicists of the 19th century thought they had the answer: the luminiferous ether. The ether was a ghostly substance, impossible to see, taste, or touch. It filled the universe completely, permeating the vacuum, carrying the vibrations of light like air carries sound. It was everywhere and nowhere at once. A silent sea in which the stars themselves floated. The ether was so subtle that it offered no resistance to planets or particles, yet so essential that without it light could not exist. For decades, the ether was accepted as fact. Textbooks spoke of it confidently. Diagrams showed light waves rippling through its invisible fabric. It was the unseen scaffold that made the world sensible. But the ether was also a kind of scientific wishful thinking, a patch sewn into the fabric of theory to preserve common sense. Because without it, waves made no sense at all. The ether was never detected, never measured, never glimpsed, and yet scientists clung to it with absolute faith. They could not imagine a universe without it. To doubt the ether was to doubt the foundation of wave theory itself. The 19th century brought extraordinary advances. James Clerk Maxwell unified electricity, magnetism, and light in a set of equations so elegant they seemed almost divine. His theory showed that light was an electromagnetic wave, a self-propagating oscillation of electric and magnetic fields. It traveled at a fixed speed, 299,792 kilometers per second, the speed of light. But this speed raised a troubling question. If light was a wave in the ether, then surely its speed must depend on how we move through that ether. Just as a swimmer moves faster or slower depending on the current, surely the Earth, racing around the Sun at 30 kilometers per second, must feel the ether's wind. It seemed an easy test. Measure the speed of light in different directions along the ether wind across it, and the difference would reveal the Earth's motion through the cosmic medium. At last, the invisible ocean would be proven real, and so two men, Albert Michelson and Edward Morley, set out to capture the ether in 1887. They built one of the most sensitive instruments ever constructed, an interferometer, a device that split beams of light and recombined them, so that the tiniest difference in speed would show up as shifting interference fringes. They waited for the Earth itself to do the experiment for them. As the planet rotated, as it orbited the Sun, the ether wind should shift, dragging light one way and then another. The fringes should shift too, revealing the Earth's invisible motion, but the fringes did not move, not a hair's breadth. The interferometer remained stubbornly silent. The ether, it seemed, did not exist. This was the collapse of certainty. A null result, nothing at all, shook the very foundations of physics. How could light be a wave without a medium? How could it ripple across the void with no fabric beneath it? The ether, the invisible ocean on which science had built its theories, evaporated like mist under the morning sun. With the ether gone, the wave model stood on the edge of contradiction. If waves demand a medium, and the medium does not exist, then what is light? The collapse of the ether was more than an embarrassment. It was an existential crisis. The entire framework of classical physics began to tremble. If the ether was gone, then either light was not a wave after all, or waves themselves behaved in ways no one could yet comprehend. Enter Albert Einstein. In 1905, a young patent clerk in Bern, working in isolation, proposed something radical. Maybe light does not need a medium. Maybe the speed of light is absolute, the same for all observers, no matter how they move. From this simple, shocking idea came the theory of special relativity, a theory that bent space and time into new shapes. Einstein's equations discarded the ether like a relic. Space itself did not need a medium. Light electromagnetic waves traveled on their own, requiring no hidden sea. The universe did not need scaffolding. It carried itself. But here is the twist. Even as Einstein destroyed the ether, he also resurrected particles. In the very same year, he explained the photoelectric effect, the way light can knock electrons off a metal surface, by proposing that light is made of quanta, discrete packets of energy, photons. And so the wave, once triumphant, suddenly had to share the stage with particles again. Nature, like a magician, had pulled off the greatest trick of all, making light wear two masks at once. Think about what this means. For centuries, humanity argued, wave or particle, Newton or Huygens, Young or corpuscles. The ether had given the wave theory its dominance, but when the ether collapsed, particles crept back in through the side door. Neither camp was right. Both were wrong. Light was both. Imagine the existential shock of that realization. The universe was no longer a machine we could diagram, no longer a puzzle that demanded only patience to solve. It was something stranger, slipperier, fundamentally contradictory. From this point forward, physics would never be the same. The collapse of the ether was not just the end of one theory, it was the end of certainty. And so, as the 20th century dawned, the stage was set for an even deeper revelation. If light could be both a wave and a particle, then what about matter itself? Could the duality extend beyond photons? Could the building blocks of atoms, electrons, protons, even the very stuff of our bodies, live in both worlds at once? That question would be answered soon, and the answer would shatter reality even further. The ether was gone. The wave, triumphant after Young's experiment, now stood without a foundation, stripped of the invisible ocean it had been thought to ride upon. Science faced a haunting contradiction. Waves without a medium, light traveling through emptiness, carrying itself across billions of kilometers of interstellar void. It was a puzzle that gnawed at the edges of reason, but worse was yet to come. Because just as the wave model seemed incomplete, an even older adversary returned to the stage: the particle. The resurrection began not with Einstein, but with a reluctant German physicist at the turn of the century, Max Planck. In 1900, Planck was wrestling with a problem known as black body radiation, the spectrum of light emitted by hot objects. According to the physics of the day, a glowing stove or a star should radiate infinite energy in the ultraviolet range, a catastrophe that clearly didn't happen. To make the equations work, Planck proposed a desperate trick. Energy could only be emitted in discrete packets, little quanta. He didn't believe it described reality. It was just math, a patch to save theory from collapse. But the patch held, and the cracks in classical physics widened. Planck had no idea what he had unleashed. His mathematical convenience would become the seed of an entirely new physics, a revolution that would rewrite reality. Enter Einstein, 1905. In one of his 4 legendary papers, the young patent clerk attacked the photoelectric effect, the way light can knock electrons free from a metal surface. If light were purely a wave, its energy should depend only on intensity, not color. Shine a dim but high-frequency light, and the wave model predicted nothing. Yet in the lab, electrons leapt free. Dim violet light could eject them, while brilliant red light could not. The energy of light was tied to its frequency, not its brightness. Einstein's explanation was audacious. Light itself comes in packets of energy, each photon carrying an amount proportional to its frequency. The higher the frequency, the higher the energy. Shine enough photons of the right kind, and electrons leap free. It was a shocking claim. Light, the quintessential wave, proven by Young's fringes, was also a particle. This was not a convenient fiction. It was experiment. It was fact. And once again, reality had betrayed common sense. Imagine the disorientation of those years. For centuries, humanity had argued wave versus particle, demanded a single truth. Now, the universe gave its answer: both. Light was a wave, spreading and interfering. Light was a particle, colliding and ejecting. It wore both masks, choosing which to reveal depending on how we dared to look. When you stare at light as a wave, it answers you with fringes and ripples. When you confront it as a particle, it answers you with collisions and quanta. The act of asking determines the truth revealed. Einstein himself was uneasy with this duality. He was not trying to overthrow the wave theory. He revered Maxwell's equations, believed in the elegance of fields. But the experiments did not lie. To explain the photoelectric effect, photons had to be real, and so, reluctantly, physics accepted that light was indivisible, granular, a stream of particles. The implications were staggering. If light, the very foundation of vision, could exist both as wave and particle, then the neat categories of classical physics were shattered. The universe was not a clockwork mechanism, but something more elusive, something that changed its form under scrutiny. What else might share this duality? If light could flicker between two identities, why not electrons? Why not atoms? Why not all of matter itself? This thought hung in the air, too daring to believe. Surely matter, solid and tangible, could not blur itself into waves. Surely the chair you sit on, the hand you raise, the breath you take, must be made of particles alone. Waves were for light, intangible and ethereal. But soon, one man would dare to extend duality to matter itself, and in doing so, he would topple reality even further. But before de Broglie, before matter waves, there was still the unsettling strangeness of the photon itself. Because if light is made of particles, why does it continue to interfere like a wave? How can photons, fired one at a time, conspire to build the very same interference fringes that once crowned Young's wave theory? It is as though each photon contains within itself both possibilities, walking both paths, interfering with its own ghost. And worse, it seems to know when we are watching. Place detectors at the slits, and the fringes vanish. The wave collapses, the particle stands revealed. Remove the detectors, and the fringes return. It is as though reality waits to decide, hanging in suspension, until we force its hand. This is not just physics, it is metaphysics. It is a question of what it means for something to exist. Is a photon a particle before we observe it? Is it a wave before we measure it? Or is it neither, living in some impossible in-between, some twilight state beyond language? The quantum birth of the photon was not a gentle revelation. It was an earthquake. Planck, Einstein, and those who followed did not solve the paradox. They made it deeper, more undeniable. By resurrecting particles within the triumph of waves, they set physics upon a path into the uncanny valley of the real. And in the decades to come, duality would not shrink. It would grow, it would spread, it would leap from photons to electrons, to molecules, to matter itself. The riddle of duality was no longer a curiosity of light, it was the fabric of existence. By the 1920s, a young French prince named Louis de Broglie would look at Einstein's photons and dare to ask the unthinkable. If waves can be particles, perhaps particles can be waves. The symmetry was too beautiful to ignore. And if de Broglie was right, then the paradox did not belong to light alone. It belonged to everything. And so, with the photon, the bridge between waves and particles was born. But the bridge was not solid, not stable. It was a trembling rope across an abyss, swaying in the winds of uncertainty. To cross it would be to enter a new world, a world where logic collapses, where probability reigns, where reality itself refuses to choose. The photon was not just a particle of light, it was the herald of a revolution. The photon had shattered certainty. Light, once thought a wave, now revealed its granular nature. The contradiction was no longer deniable, wave and particle both at once. For some, it was a temporary nuisance, a puzzle that would surely resolve with time. But for one man, the paradox was not a problem. It was a clue. Louis de Broglie was no ordinary scientist. Born into French nobility, educated in history before turning to physics, he carried the air of an outsider, a thinker unburdened by orthodoxy. Where others saw contradiction, de Broglie saw symmetry. If light could exist as both particle and wave, then perhaps duality was not a quirk of photons. Perhaps it was a law of reality itself. His question was as simple as it was revolutionary. If waves can be particles, why not particles be waves? It was a heretical thought. Matter was solid, tangible, certain. An electron was a particle, a point of charge, indivisible. A proton was mass, a nucleus, a thing. To imagine these as waves was madness. And yet the beauty of the idea haunted de Broglie. Duality, after all, should not be one way. If photons dance between wave and particle, then so should matter. De Broglie dared to write it down. He proposed that every particle of matter, every electron, every atom, everything, has an associated wavelength, inversely proportional to its momentum. The faster it moves, the shorter its wavelength. The equation was stunningly simple. Lambda equals h over p. Planck's constant, divided by momentum. That one equation implied that the solidity of the world is an illusion. Every object, every speck of matter is not just a particle, but a wave, spreading out in space, interfering with itself, rippling across reality. Pause for a moment and let that sink in. You are not just made of particles. Your body has a wavelength. Your chair, your desk, your very bones vibrate with a matter wave so small it cannot be seen, but real nonetheless. The world you thought was solid is in truth smeared, a blur, a ripple. Every particle is also a wave, and the equation is merciless. It applies not only to electrons but to protons, neutrons, atoms, molecules, planets, stars, galaxies. Everything. Of course, for large objects, the wavelength is unimaginably tiny, so small that their wave-like nature is invisible. But at the scale of atoms and electrons, the wave is everything. It governs behavior. It defines reality. De Broglie was not content with speculation. He believed his hypothesis could be tested. If electrons truly behaved like waves, then they should diffract, spread and interfere, just as light does when passed through slits or crystals. And so he proposed the experiment. Fire electrons at a crystal lattice, and their matter waves should diffract, forming interference patterns. It was bold, it was radical, it was laughable to many, but history is written by those who dare. In 1927, two American physicists, Clinton Davison and Lester Germer, working at Bell Labs, stumbled upon the answer. In a seemingly routine experiment, they fired electrons at a nickel crystal and observed the results. What they saw was shocking. The electrons diffracted, scattering in a pattern identical to waves of light. Matter, solid and indivisible, behaved like a ripple on water. The de Broglie hypothesis was no longer a dream, it was truth. The implications were staggering. The electron, a fundamental building block of matter, could no longer be described as a point, a particle, a speck. It was a wave, a smear across space, a probability cloud, something both everywhere and nowhere. The solidity of matter dissolved under the weight of the experiment. If electrons are waves, then atoms, the very structure of reality, are built not from tiny balls orbiting a nucleus, but from vibrating matter waves locked into standing patterns like the harmonics of a violin string. And suddenly, chemistry itself, the rules of bonding, the structure of molecules, the very possibility of life, makes sense only because matter is a wave. Without de Broglie's duality, atoms would collapse, chemistry would dissolve, and the complexity of existence would be impossible. Duality was no longer a riddle. It was the foundation of reality. And yet, the paradox grew deeper. Because if matter is a wave, then what does that wave represent? A ripple in space? A vibration of some hidden ether? Or something stranger? A probability wave, a mathematical ghost describing not what is but what might be. De Broglie's daring hypothesis did not end the paradox, it widened it. Matter was now caught in the same twilight zone as light, straddling particle and wave, refusing to choose. De Broglie's insight would inspire Schrodinger to write his wave equation, the beating heart of quantum mechanics, an equation that describes matter not as particles moving through space, but as waves of probability evolving in time. Reality itself dissolved into a blur of possibilities, collapsing only when observed. But for de Broglie, the triumph was bittersweet. His equation was elegant, his hypothesis vindicated, yet the mystery only deepened. Matter was not what it seemed. The universe was not what it seemed. Imagine for a moment walking through a cathedral. The arches rise above you, the sound of footsteps echoes against stone. But now imagine that sound is not a ripple in the air, but the stones themselves vibrating, interfering, diffracting, forming patterns invisible to the eye. That is the world de Broglie revealed. Not a universe of particles nor a universe of waves, but a universe where every object, every atom, every breath you take is both at once. The impossible bridge was no longer confined to light, it spanned the entire cosmos. And yet, for all its beauty, the paradox remained unresolved. Particles and waves were not reconciled. They coexisted uneasily, like two contradictory truths forced into the same sentence. The equations worked, the experiments agreed, but the meaning, the why, was still hidden. The stage was set for the next act, for Schrödinger's haunting wave equation, for the collapse of certainty, for the question that still haunts physics today. What does it mean for matter to exist as a wave until observed? The riddle was no longer a curiosity of light. It was the very essence of being. The year is 1927. The Great War has scarred Europe, industry is transforming the United States, and the world feels perched between past and future. In a laboratory at Bell Telephone Laboratories in New Jersey, two scientists, Clinton Davison and Lester Germer, are working with electrons. Their goal is not to shake the foundations of physics. They are not searching for paradoxes or revolutions. They are performing routine measurements, exploring how electrons scatter when fired at nickel crystals. But history has a way of hiding its earthquakes inside accidents. In one of their experiments, the nickel crystal they were using was accidentally oxidized. They had to heat it to restore its metallic surface. This heating rearranged the atoms inside the crystal, creating a structure perfect for diffraction. Davison and Germer didn't plan it. They didn't foresee it. But when they fired electrons at this altered crystal, the results were nothing short of astonishing. Instead of scattering randomly, the electrons formed patterns of peaks and troughs, bright spots and dark spots, interference patterns identical to those seen when waves of light strike a diffraction grating. The electrons behaved not like bullets bouncing off metal, but like ripples spreading and overlapping. The experiment confirmed what de Broglie had only dared to imagine. Electrons are waves. This was not metaphor, not analogy. It was reality. Electrons, the same particles that carry current through wires, that orbit nuclei in atoms, that form the foundation of chemistry and technology, were also waves of probability, diffracting and interfering like light through slits. The building blocks of matter, the particles that make up your body, are not points of solidity. They are patterns, vibrations, smears of possibility. Imagine looking in a mirror. You see your reflection, solid, definite, certain. But beneath the surface, your electrons are not solid at all. They are waves, overlapping, interfering, forming the very atoms of your flesh as standing patterns. You are not a machine of particles, you are a symphony of waves. The Davison-Germer experiment was more than confirmation. It was vindication. Louis de Broglie's bold hypothesis, once dismissed as the fanciful dream of a young aristocrat, now stood on unshakable ground. Matter itself was dual, both particle and wave, refusing to be one or the other. Think of the shock in 1927. For centuries, science sought clarity, singular answers. Now, the answer to one of physics' most basic questions, what is matter, was that matter is both things at once. It depends on how you look. Other experiments soon followed, each confirming the duality. Electrons fired through two slits formed interference fringes just like photons. Atoms diffracted like waves when passed through crystal lattices. Nature, it seemed, was not built from billiard balls, but from ghostly entities that shifted identity depending on how we probed them. And yet the paradox only deepened. Because when electrons are fired one at a time, separated in time so that they cannot interact, the interference pattern still emerges. Each electron interferes with itself as though it is traveling both paths at once. How can a single particle walk two roads? How can it exist in two places simultaneously? Here lies the haunting truth. Electrons are not particles or waves. They are something stranger, something beyond both categories, something that wears either mask depending on how we demand to see it. The Davison-Germer experiment pulled the curtain back on a universe that does not obey logic, but probability. Electrons spread as waves until observed, collapsing into points only when forced. Reality itself seems to hesitate, to blur, until we compel it to choose. And what is true for electrons is true for us. Every atom in your body is governed by these same rules. Every heartbeat, every breath, every thought relies on matter that is both particle and wave. You are the consequence of interference, the child of probability. Imagine shrinking yourself down to the size of an electron. The world would dissolve around you. Objects would blur into smears of possibility. Doors would not simply open or close. They would exist in both states until observed. Reality would shimmer, waiting to collapse. That is the world the electron inhabits. That is the world you are built from. The confirmation of electron diffraction was more than an experiment. It was the beginning of a revolution. For out of de Broglie's insight and Davison-Germer's proof came Schrödinger's equation, Heisenberg's uncertainty principle, and the entire strange edifice of quantum mechanics. A physics that does not describe certainties, but probabilities. Not paths, but possibilities. The particle had been dethroned. The wave had been dethroned, and in their place rose something far more unsettling. The wave function, a mathematical ghost that described reality not as it is, but as it might be. And yet, amid the triumph of discovery, there was unease. Physicists are trained to seek clarity, not paradox, to find order, not contradiction. But with electron diffraction, the contradiction could no longer be denied. Matter itself was caught in the impossible bridge, straddling two worlds. The Davison-Germer experiment won Davison the Nobel Prize in 1937, shared with de Broglie. But prizes cannot soften the disquiet, because the truth revealed in that nickel crystal is not a neat solution. It is a revelation of mystery. Imagine electrons, the scaffolding of matter, the architects of chemistry, painting interference fringes as though they were ripples of light. Imagine the solidity of the world dissolving into patterns of probability. That is what Davison and Germer discovered, not just that electrons are waves, but that reality itself refuses to be pinned down, refuses to yield to human categories. The double slit, once a curiosity of light, now belonged to matter. And if matter itself was dual, then the universe was dual. The bridge between particles and waves was not an exception, it was the rule. And so the paradox grew, unstoppable. From photons to electrons, from electrons to atoms, from atoms to molecules, the evidence mounted. The universe was not made of particles, it was not made of waves. It was made of something deeper, something that could not yet be named, only glimpsed through patterns of light and shadow. The world was changing. Certainty was dying. Physics stood on the edge of a revolution. And the next step would push it even further, to molecules so large they could almost be seen, yet still behaving like waves. The question now was not whether electrons could diffract, but whether matter itself, entire molecules, could ride the impossible bridge. Electrons were enough to shake the foundations of reality, tiny, indivisible, fundamental, and yet behaving like ripples of water. It was shocking, but perhaps tolerable. After all, electrons are unimaginably small, a billion times smaller than a raindrop. Perhaps wave-particle duality belonged only to the microscopic, a strange quirk of the unseen world. But nature is rarely content with boundaries. The paradox was not confined to electrons. It reached upward, climbing the ladder of scale, until even things we could almost see with the naked eye began to blur into waves. The story begins with a challenge. How large can an object be and still show wave-like behavior? If electrons diffract, what about atoms? And if atoms, what about entire molecules? Where does the duality stop? By the late 20th century, physicists were determined to find out. Advances in experimental technology made it possible to fire beams of not just electrons, but whole atoms, and watch their behavior. And just as de Broglie's equation predicted, atoms diffracted like waves, producing interference patterns. The atom, once the indivisible heart of matter, once thought solid and unbreakable, revealed its duality. Not only electrons, but the atoms themselves, the very bricks of existence, walked the impossible bridge. And then came the molecules. In the 1990s, scientists began firing beams of complex molecules through slits and gratings, searching for interference. The results were astonishing. Even molecules as large as Buckminster fullerene, 60 carbon atoms arranged in a perfect sphere, nicknamed buckyballs, produced interference fringes. Pause for a moment and picture this. A buckyball is not some ghostly particle. It is a molecule with mass, structure, geometry. It has weight, form, and complexity. Yet when fired through a double-slit experiment, it behaves not like a tiny soccer ball, but like a wave smeared across space, interfering with itself. 60 atoms bound together, flying as one, and somehow taking two paths at once, colliding with its own ghost. And it did not stop there. As experimental techniques improved, physicists pushed the limits further. They diffracted molecules of increasing size, 114 atoms, 430 atoms, over 800 atoms. Even these massive structures, with masses thousands of times greater than a proton, behaved like waves. Each molecule was both particle and wave, walking both roads, living in both worlds. The paradox was scaling upward, stretching the boundaries of reason. If a molecule of 800 atoms can interfere with itself, then where does it end? Could a virus? Could a bacterium? Could a human being? Nothing in the mathematics of quantum mechanics forbids it. In principle, any object, no matter how large, has a wavelength. It is just that for large objects, the wavelength becomes vanishingly small, invisible in practice. But invisible does not mean non-existent, and so the haunting thought arises. You, right now, sitting in your chair, are also a wave. Your body, your mind, your existence has a wavelength. It is so small that it cannot be measured, drowned out by the noise of your environment. But in principle, it is there. You are not only a collection of particles, you are also a blur, a probability, a ripple across space-time. Imagine a world where technology becomes precise enough to isolate a human from all interactions, all decoherence, all measurement. Imagine placing a person into a quantum experiment, firing them through a cosmic double slit. The thought is absurd, but the mathematics does not forbid it. In the right conditions, even you would diffract. Even you would interfere with yourself. What does it mean if identity itself could blur? If the self is not a singular path, but a superposition of possibilities? The experiments with molecules exposed the true strangeness of the universe. Duality was not a trick reserved for photons and electrons. It was universal. Every object, no matter how complex, carries within it a wave. The paradox belongs to everything. And yet here lies the deeper mystery. In practice, we do not see people diffract. We do not see chairs interfering with themselves. Why not? What changes between the quantum world and the classical? Where is the boundary? This is where decoherence enters the stage. The larger an object, the more it interacts with its environment, with air molecules, with photons, with vibrations. These interactions force the wave function to collapse, destroying interference. The object behaves as a particle, fixed and definite, not because it has no wave, but because the wave is drowned in a sea of entanglements. The macroscopic world is quantum, but it is quantum obscured by its own complexity. The line between quantum and classical is not a boundary written into nature. It is a blur, a gradient. The paradox is everywhere, hidden only by the noise of existence. The experiments with molecules did more than prove de Broglie right. They proved that the wave nature of matter is universal, stretching upward into scales where intuition collapses. They revealed that the duality is not a curiosity, not an exception. It is the law. Think of it this way. When you walk through a doorway, you believe you chose one path. But in the mathematics of quantum mechanics, every particle of your body explores all paths. Your existence collapses into one outcome only when the world forces the choice. The rest remain as ghosts, unmeasured, unseen, but part of the wave function of the universe. And so, as the 20th century closed, physicists found themselves staring into a new abyss. The paradox had grown from photons to electrons, from electrons to atoms, from atoms to molecules. At each step, the bridge between particles and waves held. At each step, the world became stranger. And now a question loomed like a specter. If everything is a wave, what is the wave made of? What is it that oscillates, spreads, interferes? If there is no ether, no medium, then what is waving? Probability, possibility, or something deeper, beyond human comprehension? The riddle had expanded, and the next step would make it darker still, for it was not only the wave that was strange, but its collapse. The sudden and inexplicable way possibility becomes certainty. The paradox was not yet complete. It was only beginning. By the late 1920s, physics had crossed the threshold. Duality was no longer speculation, no longer an oddity. Photons, electrons, atoms, even vast molecules, all were found to straddle the line between particle and wave. The impossible bridge was not the exception, it was the rule. But if that was true, then a new and more terrifying question emerged. What exactly is the wave? For centuries, waves were understood as disturbances of something tangible. Water waves ripple through water, sound waves vibrate air. But the wave of matter was different. It had no medium. It was not a ripple of substance, but of possibility. The mathematics hinted at this, but it would take the mind of Erwin Schrodinger to make it explicit. In 1926, Schrodinger proposed an equation that would become one of the most famous in science, his wave equation. At its heart lay a radical claim. Every particle is described not by a fixed trajectory, not by a path carved through space, but by a wave function, a mathematical entity that spreads out, evolves, and interferes. This wave function does not describe where the particle is. It describes where it might be. Reality, it seemed, was not made of certainties. It was made of probabilities. The electron in an atom was not circling the nucleus like a planet around the sun. It was a cloud of possibility, smeared across space, existing everywhere until observed. Picture it. An electron is not here or there. It is a blur, a haze, a ghost that fills the atom, spread thin until the moment you look. Only then does it collapse into a single point, a single place. The act of observation seems to carve certainty out of possibility, to force the wave function to resolve. Before the measurement, reality is indeterminate. After it, reality is fixed. The collapse of certainty. The world does not exist in definite states until interaction forces it to. Schrodinger himself found this unsettling. To dramatize the absurdity, he proposed his famous thought experiment, a cat sealed in a box with a device triggered by quantum decay. If the particle has a 50% chance of decaying, then until observed, the cat is neither alive nor dead, but both. A superposition, just like the electron in its cloud. The wave function describes both possibilities at once, existing in a twilight zone until we dare to look. It is one of the most haunting ideas in science. Reality itself seems unfinished until observed. Certainty does not precede measurement. It is created by measurement. What then is the wave function? Some physicists treated it as a tool, a mathematical trick useful for predictions but not real. Others saw it as the very fabric of existence, a probability field that underlies reality itself. In either case, the message was clear. The world is not what it appears to be. Beneath the surface lies a blur, a smearing, a ghostly cloud of maybes. Quantum mechanics does not describe things, it describes chances. It tells us not where the electron is, but where it is likely to be. And yet, when we measure, we always find the electron somewhere, definite, real. The bridge between possibility and certainty is the collapse of the wave function, sudden, mysterious, unexplained. The implications are dizzying. The solidity of the world is not solid at all. The table beneath your hand exists as a web of probabilities until interactions, collisions of photons, touches of electrons, force it into reality. You are not walking through a world of certainty. You are walking through a storm of possibilities, collapsing into facts only as they are encountered. This is not philosophy, it is experiment. Double slits, diffraction, interference, all confirm it. The collapse of the wave function is not speculation, it is what the universe does. And yet, the collapse is nowhere to be found in the equations. Schrödinger's wave function evolves smoothly, like ripples on a pond, until suddenly, without warning, it snaps into certainty. The mathematics cannot explain when or how this happens. The act of observation, whatever it is, lies outside the equation. This gap, this blind spot at the heart of physics, is the wound that still bleeds today. What causes collapse? What counts as an observation? Does consciousness play a role? Or is observation just another word for interaction, for entanglement, for the environment itself forcing the choice? Schrödinger's cat is not just a thought experiment, it is a mirror. It reflects the absurdity of a universe that exists in limbo, undecided, until something or someone forces it to choose. Imagine reality as a book, but one written in disappearing ink. The words are there in potential, but they only darken, become readable when you turn the page and shine light upon them. Until then, the story is not fixed. Every outcome coexists, every ending is possible. Only when you look does the ink commit itself. This is the quantum world, and this is the collapse of certainty. The paradox is staggering. Physics, the science of objectivity, now insists that reality is not fully real until observed. The observer, once banished from the equations, now lurks at the center. The act of looking changes what is. The act of measuring creates reality. What does this mean for truth? What does it mean for existence itself? Are we discovering reality, or are we helping to make it? The collapse of certainty is more than a scientific riddle. It is an existential one. Because if observation shapes reality, then we are not passive witnesses of the universe. We are participants in its becoming. Every glance, every touch, every measurement writes a line of the cosmos into permanence. And yet, the wave function itself, the ghost of possibility, remains hauntingly real. It continues to evolve, to spread, to interfere, even when no one is watching. It is as though reality contains two layers, the shadow world of probabilities and the surface world of facts. The collapse is the bridge between them, the moment when shadow becomes substance. But no one knows how, no one knows why. And so, as quantum mechanics rose triumphant, its victories were shadowed by unease. The experiments worked, the mathematics matched, but the meaning was elusive. The wave function collapse was a riddle wrapped inside reality itself, an unanswered question at the core of existence. The paradox was no longer confined to photons and electrons. It was now woven into the fabric of reality. And the next step, the role of the observer, the ghostly shadow of consciousness, would only deepen the mystery. The wave function collapse had opened a wound in physics. Schrödinger's cat was not a joke, it was a warning. The mathematics of quantum mechanics described a world of shadows, of overlapping possibilities, but it could not explain why those shadows dissolved into certainty only when observed. Observation, once a passive act, had become a force, a shadow stretching over reality itself. But what is an observation? Imagine the double-slit experiment again, the stage upon which the universe plays its cruelest tricks. Fire photons one by one through the slits, and over time they build the haunting interference pattern, the unmistakable signature of waves. But place detectors at the slits, tiny devices to mark which path the photon takes, and the interference vanishes. The fringes dissolve, the wave collapses. The photon chooses a slit, a path, a place. The very act of measuring forces it into a single truth. Light behaves like a wave when we do not watch, but like a particle when we do. Reality seems to care whether we are looking. It is as though the photon senses the question we are asking and changes its answer accordingly. Ask it, "Are you a wave?" and it replies with interference fringes. Ask it, "Which slit did you pass through?" and it replies with a single path. But never both. The universe refuses to reveal its full face at once. The act of asking defines the reality we receive. The observer cannot stand apart. The observer is written into the script. Physicists wrestled with this revelation. What counts as an observer? Is it a conscious mind, a human being? Or is it any interaction with the environment, any entanglement with the wider universe? Does a photon striking a detector count as observation, or must it be registered in the mind of a scientist? This was not philosophy. It was physics clawing at its own foundations. The Copenhagen interpretation, championed by Niels Bohr, declared that quantum mechanics does not describe reality as it is, but only as it is observed. The wave function is not a physical object, but a tool, a map of probabilities, collapsing when measured. For Bohr, questions about the underlying reality were meaningless. Physics was about outcomes, not hidden truths. But others, like Einstein, were horrified. "Do you really believe the moon is not there when you are not looking at it?" he asked. To him, physics without an objective reality was an abdication. The universe must exist independent of observation. The alternative was madness. And yet, experiment after experiment sided with Bohr. The double slit, with or without detectors, behaved exactly as the Copenhagen interpretation predicted. The shadow of the observer could not be denied. The observer's shadow stretches across time itself. In some versions of the experiment, detectors are added or removed after the photon has passed the slits, and still the outcome changes. It is as though the decision to observe rewrites the past, collapsing not only the wave, but the very history of the particle. This is Wheeler's delayed choice experiment, a haunting suggestion that reality is not fixed until the question is asked, even if the question is asked after the fact. Observation, it seems, reaches backward as well as forward. Imagine the implications. The past is not settled. The present is not fixed. The universe waits, undecided, until observation pins it down. Reality is not a book already written, but a manuscript constantly being edited, its sentences rearranged by the act of reading. Are we discovering the world, or are we creating it? The observer's shadow is not an invitation to solipsism, the idea that reality exists only in our minds. It is deeper than that. It is the recognition that reality is participatory. The universe is not a stage upon which we stand as passive spectators. It is a play in which we are actors, our questions shaping the script, our measurements collapsing the possibilities into facts. And yet, the nature of this participation remains elusive. Is consciousness required? Does the human mind possess some unique role in the collapse of the wave function? Or is observation nothing more than interaction, any exchange of information, any entanglement with the environment? Physicists disagree, and to this day, the question remains unresolved. Some interpretations whisper that consciousness is fundamental, that reality itself requires awareness to crystallize. Others insist that no, collapse is merely the inevitable consequence of systems interacting, of information being exchanged. The observer is not mystical but mechanical. Still, the unease persists. Because even if collapse is mechanical, it remains a mystery. Why does a wave of possibilities collapse into a single certainty? Why one outcome and not another? What is the mechanism? The mathematics is silent. The shadow remains. The observer's shadow suggests that the universe may not be wholly external, wholly objective. It may be relational, participatory, unfinished without us. Imagine walking into a darkened room. The furniture exists, but until you switch on the light, its placement is unknown. Now imagine that when the light comes on, the furniture does not merely become visible, but actually arranges itself in response to your gaze. That is the unsettling implication of the observer's role in quantum mechanics. And here lies the haunting truth. The act of observing is not passive. It is active. To measure is to intervene. To observe is to collapse. To look is to shape reality itself. This is the observer's shadow. Long, inescapable, stretching across every experiment, every equation, every attempt to pin down the quantum world. It is the realization that the universe is not a cold machine, ticking away indifferent to us, but a paradoxical stage upon which our very presence changes the play. And so physics stood divided. Some embraced the Copenhagen interpretation, pragmatic, unsatisfied but functional. Others searched for hidden variables, unseen layers of reality that might restore objectivity. But the experiments refused to yield. The observer's shadow remained. The paradox deepened. Reality was not merely dual, it was relational. It did not exist in isolation but in dialogue, and the dialogue was still ongoing. The next act would take the paradox further, into experiments that seemed to rewrite the past itself. Delayed choice, quantum erasers, demonstrations so haunting, they suggested that causality itself might not survive the quantum world. The bridge between waves and particles was not only impossible, it was temporal, bending not just reality, but time. The observer's shadow had already unsettled physics. But what if the influence of observation was not confined to the present? What if our choices today could reach backward in time, reshaping the past itself? This is the nightmare hinted at by John Archibald Wheeler's delayed choice experiment, one of the most haunting ideas in all of science. Imagine again the double-slit experiment. A photon is fired toward two slits, and, as always, it faces its riddle, particle or wave. If both slits are open and unobserved, it builds an interference pattern, a signature of wave-like behavior. If detectors mark which slit it passes through, the fringes vanish, and the photon behaves like a particle. This much we know. Now, Wheeler adds his twist. Suppose we delay the decision about whether or not to observe until after the photon has already passed the slits. By all logic, the photon should already have chosen. Its history should be fixed. And yet, when the experiment is done, the outcome reflects the choice made after the fact. If detectors are activated, the photon appears to have taken a single slit. If they are not, it appears to have passed through both and interfered. The present seems to reach backward, altering the past. The photon's decision about how it traveled depends on a measurement made only after its journey should have been completed. It is as though the photon lives in suspense, its history unwritten until we ask. Observation does not merely collapse the present, it rewrites the timeline. And the haunting implication is this: perhaps the past is not fixed. Perhaps it too exists as a superposition, a blur of possibilities, waiting to be collapsed by future choices. Causality, the bedrock of reason, begins to crack. The arrow of time itself bends under quantum pressure. But Wheeler's thought experiment was only the beginning. In the 1980s and beyond, physicists carried out versions of the delayed choice experiment with actual photons, and the results matched Wheeler's eerie prediction. The choice of whether to measure wave or particle behavior, even when made after the photon should have decided, determines the outcome. Nature waits. Reality is not written until the question is asked. As if that were not enough, physicists added another layer, the quantum eraser. The quantum eraser experiment begins like the double slit. Photons pass through slits, and detectors record which path they take. As expected, the interference pattern vanishes. Particles stand revealed. But then, the which path information is erased. The data is scrambled, destroyed, made unknowable, and suddenly the interference pattern returns. The fringes reappear as though the photons never revealed their paths. The very knowledge of which path the photon took, the information itself, determines the outcome. If the information exists, the wave collapses. If the information is erased, the wave returns. Knowledge itself is the switch that controls reality. It gets stranger. In some variations, the erasure is performed after the photons have already hit the screen. Yet still, the interference pattern can be recovered. Once again, the present seems to reach backward, reshaping what has already happened. Imagine this. The photon strikes the detector. The dot is fixed. The event is real. But later, the act of erasing or preserving which path information determines whether those dots assemble into interference fringes or particle scatter. The past is not simply recorded, it is rewritten. What then is history? Is it a film already shot, frames fixed in sequence? Or is it a story still being written, malleable, waiting for choices yet to be made? Wheeler himself suggested that perhaps the universe is participatory, that the present choices of observers help bring the past and even the cosmos itself into existence. It is a dizzying thought, one that stretches science into philosophy, physics into metaphysics. Imagine standing at the edge of the Grand Canyon, gazing at rock layers carved over millions of years, solid, ancient, immutable. And then imagine being told that those layers may not be fixed until observed, that the past of the canyon, the fossils within, the history they record, all exist in a quantum blur until entangled with the act of measurement. It feels impossible. And yet the photon in Wheeler's experiment lives in just such a state. The quantum world does not just challenge our sense of space, it challenges our sense of time. The future reaches into the past. Cause and effect become tangled. The universe refuses to obey our most basic intuition. Some interpretations of quantum mechanics accept this outright. They claim that reality is not a fixed sequence of events, but a web of possibilities, with observation collapsing both present and past into consistency. Others resist, searching for ways to preserve causality, to protect the arrow of time. But experiment after experiment continues to suggest that nature plays by rules far stranger than we imagined. The quantum eraser, in particular, whispers something haunting. That information itself is fundamental. Not matter, not energy, but knowledge. What is known or can be known shapes what is real. And when information is destroyed, reality shifts to match. It is not consciousness alone that matters, but the possibility of knowledge, the structure of information embedded in the universe. Physics, it seems, is not about things, but about what can be said of things. Reality is not just participatory, it is informational. The photon does not simply travel, it waits to see what can be known of its journey. The world is not made of objects, but of relationships, of entanglements, of knowledge itself. The delayed choice and quantum eraser experiments leave us with a universe more slippery than ever. Space and time dissolve into shadows. Causality bends, information reigns, and through it all, the impossible bridge between waves and particles remains the stage upon which these mysteries play. Imagine looking into a mirror. You see yourself, solid, present, undeniable. But beneath that reflection lies a ghostly uncertainty. Your past, your very history, may not be as fixed as you believe. Perhaps it waits, like the photon, for the question you have yet to ask. This is not science fiction. It is experiment. It is fact. And it is one of the most unsettling truths humanity has ever uncovered. Reality itself is unfinished until observed. The paradox has grown beyond duality. It has swallowed time. The impossible bridge does not just span particles and waves. It spans past and present, cause and effect, knowledge and existence. And now physics faced a new crisis: how to interpret this madness. Was the Copenhagen view correct? That reality has no hidden truth beyond observation? Or were there other possibilities, other worlds, other interpretations, that might explain the riddle? The next chapter would be a battle of worldviews, as physicists tried to peer behind the mask of duality and find what, if anything, lay beneath. By the late 1920s, quantum mechanics was no longer speculation. It was fact. Experiments confirmed it. Equations predicted it. The theory worked with brutal precision, explaining phenomena that classical physics could not touch. And yet, no one could say what it meant. The wave function described a blur of possibilities, collapsing into a single outcome when observed. But why? How? What was collapsing? And what role did the observer truly play? These were not small questions. They were cracks in the foundation, cracks that grew wider with every experiment. Different minds offered different answers, and each answer became an interpretation, a worldview, a lens through which to glimpse the quantum riddle. None could claim victory. All were haunted by contradictions. Let us walk among these competing visions. The first and most dominant was the Copenhagen interpretation, born in the mind of Niels Bohr. To Bohr, the wave function was not a picture of reality. It was a tool, a probability map, a way of predicting outcomes. To ask what the electron really is before measurement is to ask a meaningless question. Physics does not reveal an objective world. It only describes what we observe. Reality, in Bohr's view, is not what is. It is what is measured. Under Copenhagen, the universe is mute until we interrogate it. The electron does not have a position until we measure one. The photon does not choose a path until we ask. The act of questioning is the act of creating. This interpretation was pragmatic, functional, and deeply unsettling. It made no attempt to explain the mechanism of collapse, only to declare that the question itself may be unanswerable. Shut up and calculate, later generations of physicists would say, tired of philosophy. But the unease never faded. Against Bohr stood Albert Einstein. He refused to accept a universe built on probabilities and collapses. God does not play dice, he insisted. For Einstein, the wave function was incomplete, a shadow cast by deeper, hidden variables. Beneath the blur, reality must be definite, objective, real. The moon does not vanish when unobserved. Einstein's rebellion gave birth to hidden variable theories, attempts to restore determinism to quantum mechanics. Among them was David Bohm's pilot wave theory, a vision in which particles are always real, always definite, guided by an invisible wave that steers their paths. In this picture, the wave never collapses. The particle rides it like a ship on an unseen sea, hidden variables charting the course. Then came the most audacious vision of all, the many worlds interpretation. Proposed by Hugh Everett in the 1950s, it rejected collapse entirely. The wave function never shrinks. Every possibility persists. When a photon chooses one slit, the other choice is not destroyed. It is realized in another branch of reality. When you measure an electron's spin, one outcome is recorded in your world and another in a parallel world where you too exist but see a different result. Under many worlds, the universe is constantly splitting, spawning infinite realities with every quantum event. In one world, you are watching this documentary. In another, you never clicked it. In yet another, you never existed. It is a vision both terrifying and seductive. It rescues determinism by banishing collapse, but at the cost of an infinite multiverse, a cosmos where every possibility is real. Which is more unsettling? A universe unfinished until observed, or a universe that endlessly fractures, spawning countless versions of you with every breath? Others tried different paths. Some argued that collapse is real but objective, not tied to observers, but to physical processes. When systems grow too complex, the wave function collapses on its own, washing probabilities away into certainty. This was the idea behind objective collapse theories like those of Girardi, Rimini, and Weber. Still others pushed further into philosophy. Could consciousness itself be the trigger? Could awareness be the spark that collapses waves into facts? If so, then the mind is not a bystander but a participant woven into the fabric of reality. It is an idea both thrilling and dangerous, veering toward mysticism but never fully banished. None are proven, all remain possible. The competing interpretations are not just theories, they are mirrors reflecting the limits of human imagination. Each is a way of saying, we cannot comprehend what the universe is showing us, so we will choose a mask to wear. But the masks never quite fit. The paradox leaks through. And here lies the haunting truth. Quantum mechanics works. It predicts outcomes with precision unmatched by any other theory. It builds lasers, transistors, computers, GPS, the modern world. Yet we do not know what it means. The equations hum with accuracy, but the story behind them remains a riddle. It is as though we are reading a script written in a language we do not understand, a language that delivers answers without meaning, certainty without explanation. What then is reality? A probability cloud that collapses when observed. A hidden dance of particles guided by waves we cannot see. An infinite sea of worlds, each as real as ours. Or something stranger still beyond all interpretation, physics cannot yet say. And so the paradox deepens. The impossible bridge between particles and waves has become an impossible bridge between interpretations, between visions of reality. Each physicist stands on a different shore, gazing across the gulf, trying to glimpse the truth. But the truth remains veiled, shimmering like interference fringes on a screen. And the question grows darker still. Perhaps particles do not exist at all. Perhaps waves themselves are illusions. Perhaps reality is built not from things but from something deeper. Fields, vibrations, excitations, patterns that defy the categories we cling to. The next step in our journey is not about interpretations, but about erasure. The possibility that particles are not fundamental at all, but illusions conjured by the mathematics of fields. The paradox is about to cut deeper. For centuries, physics imagined the universe as a mosaic of particles, tiny, indivisible grains of matter, colliding and combining, building everything from stars to skin. The atom, the electron, the photon, these were the things of reality, the ultimate bricks in the cosmic wall. But quantum mechanics, with its contradictions and its blurred wave functions, began to gnaw at that picture. And then came the most radical possibility of all. What if particles do not exist? The 20th century gave birth to a new language, quantum field theory. It whispered that the world is not made of particles but of fields. Invisible fields stretch across the universe, permeating space, endless and continuous. Particles in this view are not fundamental. They are ripples, excitations, local disturbances in the sea of fields. Imagine the surface of an ocean. A wave rises, crests and falls. To the eye, it seems like a thing, a moving object. But the wave is not separate from the ocean. It is the ocean, expressing itself in motion. So it is with particles. An electron is not a little bead orbiting a nucleus. It is a ripple in the electron field. A photon is not a grain of light, but an excitation of the electromagnetic field. Every particle is a crest upon an invisible sea. The solidity of the world is an illusion. What we call particles are temporary ripples, fleeting excitations in endless fields that cannot be seen. This is not speculation. Quantum field theory is the most successful framework in science. It predicts the magnetic moment of the electron to 12 decimal places. It gives us the standard model, a catalogue of fields whose excitations appear as particles, quarks, leptons, bosons. The Higgs boson itself was found as nothing more than a ripple in the Higgs field, glimpsed for a heartbeat at CERN, before dissolving again into the sea. When you touch the world, you are not touching particles. You are touching vibrations, resonances, standing waves upon fields that fill the void. The universe is not a machine of billiard balls, but a symphony of oscillations. And yet, the paradox remains. Because experiments still reveal particles, electrons detected one by one, photons striking a screen, atoms leaving discrete traces. The illusion is stubborn. The world still behaves as though particles are real, and so we are left with a dual picture, fields beneath, particles above. The question is not whether one is true and the other false, but how both can be true at once. What then is a particle? A point-like entity, indivisible, or an emergent pattern, born from fields like foam riding the crest of a wave? Consider this. When two electrons collide in an accelerator, the mathematics of field theory does not describe particles bouncing like marbles. It describes quantum fields interacting, their excitations exchanging energy. What we see as particles are the aftershocks, the ripples left behind. Perhaps particles are not things at all, but events, temporary excitations, appearing and disappearing, leaving only traces. This view is deeply unsettling. The idea that the universe is made of stuff is ancient, intuitive, comforting. But field theory strips that away. It tells us the world is not built from things, but from processes, not objects, but interactions. Existence is not substance, but activity. And in this light, wave-particle duality looks different. A photon is not a particle, nor a wave. It is a ripple in a field which can manifest as interference in one experiment or as discrete impacts in another. The duality is not a contradiction. It is a symptom of trying to force a deeper reality into categories it does not fit. Wave and particle are masks, human metaphors for something stranger, a reality made not of things but of excitations. Think of music. A note is not an object, it is a vibration, a resonance in the air. It exists, yet it has no solidity. The universe, in the language of quantum field theory, is music made visible. Particles are notes, fields are instruments, and reality is the symphony they play. But even this vision leaves haunting questions. If particles are illusions, what are fields themselves? They stretch through space, yet cannot be seen. They vibrate, yet cannot be touched. They are real, but intangible. Are they substance? Or are they mathematics, equations written into the void? Perhaps even fields are not ultimate. Perhaps they are not the foundation, but another layer of illusion, hiding something deeper still. Strings, loops, holograms, physics continues to search for a more fundamental picture, a truer description of the ocean beneath the ripples. But what if there is none? What if reality is not built from ultimate stuff at all, but is fundamentally relational? Patterns of information woven into a self-sustaining web. If particles are illusions and fields are equations, then perhaps what is real is not substance, but mathematics itself. The universe as a structure of relationships, a pattern that exists not in space, but as space. And so the riddle deepens. The bridge between particles and waves may be an illusion, because particles and waves themselves may be illusions, shadows of a deeper, nameless reality. What if the solidity of your hand, the warmth of sunlight, the very sense of existence, is nothing more than interference patterns in fields, ripples of probability in equations that care nothing for substance? This is the unsettling truth whispered by modern physics, that the things we cling to are not things at all. The electron is not a point, nor a wave. It is a ripple. The photon is not a particle, nor a wave. It is an excitation. You are not a body of particles, but a standing wave of fields, stabilized by probabilities. And if particles are illusions, then so is the very concept of thingness. Reality is not made of things. It is made of events, patterns, relationships. The next step in our journey will push this paradox even further. For if particles are illusions, then so too is the certainty of the macroscopic world. The duality may stretch not only across matter, but across scale, raising the question of why we, who are made of waves, do not see our own wave nature. The bridge between particles and waves is not the only impossible one. There is another, between the quantum and the classical, the micro and the macro, the blurred and the solid. And to understand it, we must explore the limits of duality itself. By now, the riddle had spread across the cosmos. Light, electrons, atoms, even molecules, all walked the impossible bridge between particle and wave. Field theory stripped particles of their solidity, leaving only ripples, excitations, ghosts in a deeper sea. And yet, if this is the truth of the universe, then a haunting question arises. Why do we not see it? Why does the everyday world look so solid, so definite, so certain? Look around you. The table does not blur. The chair does not diffract. The coffee in your cup does not interfere with itself. We do not experience our lives as smeared probabilities. We experience them as facts. You are here, not there. Alive, not dead. Awake, not asleep. The wave dissolves into certainty long before it reaches the scale of human experience. And so we are forced to ask, where are the limits of duality? Why does quantum strangeness govern the micro world, yet vanish in the macro? The answer, or at least the beginning of one, comes in a concept called decoherence. Imagine a violin string vibrating in a darkened concert hall. Alone, its note is pure, resonant, sustained. But now imagine hundreds of other instruments joining in, each vibrating, colliding, clashing. The single note is drowned in a cacophony, its clarity lost. So it is with quantum systems. An isolated electron can diffract, interfere, exist in superposition, but as soon as it interacts with the wider world, with photons, with air molecules, with heat, with you, its delicate wave function entangles with the environment. The pure quantum state decoheres, breaking apart into a blur of interactions. What remains is the classical world we see. Definite, solid, certain. The solidity of the world is not the absence of quantum behavior. It is the drowning of it. The blur is still there, but hidden beneath layers of entanglement. Decoherence explains why a molecule can diffract, but a chair cannot. Why electrons smear into probability, but you do not. Large systems with countless particles interact so constantly with their environment that their quantum nature is washed away before it can be glimpsed. Reality, as we experience it, is the wreckage left by the collapse of coherence. But decoherence is not the end of the mystery. It explains why quantum effects disappear at larger scales, but it does not solve the paradox of collapse. The wave function still spreads, the probabilities still exist. Decoherence merely buries them under noise. It tells us why we cannot see superpositions in the macroscopic world, but not why one outcome is chosen over another. The riddle remains. The world looks classical not because it is, but because quantum truth is hidden from us, drowned beneath its own complexity. And so the limits of duality are not walls, but veils. Every object you see, the table, the chair, the hand you raise, still has a wave function, still exists in superposition. But the entanglement with the environment is so vast, so immediate, that the blur resolves before our eyes can detect it. You are quantum, you are wave, you simply cannot see it. What if we could remove decoherence? What if we could isolate a cat, a human, even a planet from every interaction? Would it diffract like an electron, interfere with itself, exist in superposition? The mathematics says yes. The experiment is impossible, for now. But the thought lingers, haunting. The limits of duality also raise deeper questions. Is the boundary between quantum and classical sharp or gradual? Does the wave function collapse suddenly, like a cliff, or fade like a shoreline? No experiment has answered. We live suspended between two pictures, unable to say where one ends and the other begins. And this uncertainty is not academic. It cuts to the heart of reality. If duality has no limit, then the universe itself may be a superposition, a wave smeared across possibilities. If duality ends somewhere, then the question becomes, who or what enforces that end? Does collapse occur naturally, or is it tied to observation, to knowledge, to consciousness? The limit of duality is the limit of reality itself. To ask where duality breaks is to ask where existence becomes definite. Consider this image, the night sky filled with stars. Each photon of starlight travels billions of years to reach your eye. Along the way, it exists in superposition, both particle and wave, both path and possibility. Only when it strikes your retina does it collapse, deciding finally its history. For billions of years, its state was undecided, and you, simply by looking, complete its journey. This is the scale of the paradox. The collapse of duality is not confined to laboratories, it is written into the cosmos itself. The universe is a blurred story, and only in the act of reading does the ink settle into words. Decoherence helps us understand why the strangeness fades as systems grow large, but it cannot silence the haunting question, is the solidity of the world an illusion? Do we live in a universe of waves pretending to be particles, probabilities pretending to be facts? And if so, what does that mean for us? Are we also superpositions collapsing into identity only through the constant measurement of the environment? Are we waves of possibility entangled with the universe, shaped into solidity by the act of living? If we are quantum, then what is the self? A definite being or a blur of possibilities collapsed by the world's gaze? The limits of duality are not boundaries to be drawn on a map. They are mysteries, shifting, elusive, unfinished. The world looks solid not because it is, but because we are too entangled to see the truth. The wave never dies. It is simply hidden, buried beneath the noise of existence. And so we arrive at the precipice. Duality has climbed from photons to electrons to atoms to molecules, up toward the macroscopic world. Decoherence veils it, but does not erase it. The bridge remains. The next step is philosophical, perhaps inevitable. If duality is the rule, if decoherence only hides it, then perhaps the paradox is not a flaw to be resolved, but the essence of reality itself. Perhaps duality is not contradiction, but truth. The stage is set for the impossible bridge to reveal its deepest meaning, not as a puzzle to solve, but as a mirror reflecting the nature of existence. For centuries, physics sought clarity. Newton gave us particles marching through space. Maxwell gave us waves filling the void. The universe seemed ordered, intelligible, its laws crisp and eternal. But quantum mechanics shattered that dream. Now, at the heart of reality, we find not clarity but contradiction, not particles, not waves, both, neither, something stranger than either. The impossible bridge has haunted us from the first slit of light to the diffraction of buckyballs, from Schrodinger's equation to Wheeler's delayed choices. Each step only deepens the riddle. We asked the universe to tell us what it is made of, and it answered with paradox. Perhaps the paradox itself is the answer. Consider what wave-particle duality reveals. That reality is not one thing, but two incompatible faces, revealed only when demanded. A photon behaves like a wave if we look for waves. It behaves like a particle if we look for particles, but never both at once. The question defines the answer. It is as though reality is a mask that shifts depending on the gaze. One mask, then another, but never the face beneath. We have built equations that predict the masks with perfect accuracy, yet the face itself remains hidden. What is the true nature of the thing behind the mask? We cannot say. Some call it the wave function, a mathematical phantom that evolves smoothly until forced into certainty. Others call it information, the currency of what can be known. Still others whisper of hidden layers, unseen worlds, or infinite branches of possibility. But perhaps the deeper truth is this: there is no hidden thing at all. Perhaps the paradox is not a puzzle to solve, but a window into the nature of existence itself. Reality, in this view, is not a fixed object. It is a relationship. It is not the thing, but the question. Not the particle, not the wave, but the dialogue between observer and observed. To exist is not to be one or the other, but to be both, waiting to be called forth. Imagine standing on a bridge suspended over an abyss. On one side, particles, definite, solid, countable. On the other, Waves, continuous, spread, infinite. Physics stands in the middle, unable to step fully to either side, forced to accept that both shores are true, and in the tension between them lies the mystery of the universe. But the bridge is more than contradiction, it is possibility. Because in forcing us to abandon certainty, it invites us into wonder. What else might the universe be if not particle or wave? What new categories unknown to human thought might lie beyond? There is a story in this paradox, not of defeat, but of humility. For perhaps reality is not built to fit the boxes of human logic. Perhaps the universe is not obliged to be comprehensible. And yet, in its refusal to yield, it gives us something greater than comprehension. Awe. Think again of the double slit. A photon travels unseen. Is it a particle? A wave? We do not know. The moment we ask, it chooses. But until then, it is both, or neither, or something else entirely. That single experiment, simple and austere, contains the whole mystery of existence, a riddle without resolution, a bridge without end. And here is the thought that lingers. If the building blocks of reality are contradictions, then perhaps reality itself is contradiction. Perhaps existence is not unity, but duality, light and dark, wave and particle, possibility and certainty, forever entwined. We are accustomed to thinking of paradox as failure, but what if paradox is the truth? What if reality is not simple but irreducibly strange? What if the bridge is not meant to be crossed but lived upon? Close your eyes and feel your breath. Every atom in your lungs, every electron in your blood, every photon striking your skin exists in this dual state. You are not solid, you are not wave, you are both. You are possibility collapsing into certainty moment by moment. You are the paradox made flesh. The impossible bridge is not out there in laboratories or equations. It is here, in you. You walk it with every thought, every heartbeat. You are its child. And perhaps this is the final revelation, that the paradox is not a problem to be solved, but a truth to be accepted. That reality is stranger than logic, deeper than categories, more haunting than comprehension. That existence itself is the impossible bridge, spanning particles and waves, past and present, knowledge and being. The universe does not offer us clarity, it offers us mystery. And in that mystery, it invites us not to conquer, but to wonder. The bridge stretches onward, whether it leads to hidden variables, to infinite worlds, to deeper fields, or to truths we cannot yet imagine, no one can say. But we are on it. We have always been on it, and the only way forward is to walk deeper into the unknown. How can something be a particle and a wave at the same time? It was the question we began with, and after all the experiments, all the equations, all the interpretations, it remains unanswered. The riddle is not resolved. It is eternal. Every beam of light, every electron in motion, every atom in your body whispers the same contradiction. They travel like waves, yet arrive like particles. They spread across space, yet strike as points. They smear into probability, yet collapse into certainty. They refuse to choose a single identity because perhaps there is no single identity to choose. And so we circle back to the beginning, to the double slit, to the interference fringes, to the haunting realization that reality wears two masks and never shows its face. We are made of this strangeness. The blood in your veins flows with particles that are not particles, with waves that are not waves. The solidity of your hand, the breath in your lungs, the spark of your thoughts, all are woven from dual entities, straddling two realities at once. You are the bridge, the contradiction embodied. Science has not solved this mystery. It has only revealed it more clearly. We now know the rules of the game: wave functions, probabilities, decoherence, entanglement. But beneath the rules lies the riddle that endures. What is a photon? What is an electron? What is anything? The deeper we look, the stranger it becomes. Perhaps this is the lesson. Science does not erase mystery. It sharpens it. Each answer births a deeper question. Each discovery opens another abyss. We build bridges of mathematics, but the chasm does not close. The paradox remains, infinite and inexhaustible. And yet there is beauty in this. Because mystery is not failure, it is invitation. The paradox is not a dead end, it is a frontier. We live in a universe that does not give us the comfort of clarity, but the wonder of strangeness. A universe where certainty is born only in the act of observation, where the past itself may wait to be written, where reality sings with possibility until forced into form. Think of that. The world you see is not the only world that could have been. Behind every photon, every atom, every moment lies a blur of unrealized histories, a chorus of might-have-beens collapsed into what is by the simplest act of looking. You are not only in the universe, you are part of its becoming. And so the riddle remains, not as a taunt, but as a gift. For in that riddle lies the wonder of being alive in such a cosmos. To walk through existence knowing that at its foundations, reality is stranger than imagination, stranger than reason, stranger than truth. We began with a question, we end with awe. The universe does not whisper answers. It sings in paradox. Thank you for joining us on this extraordinary journey through the universe here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us where we unravel the darkest mysteries of space.